Welcome, Universal System Administrators, to today's Explainer. We're going to dive straight into the absolute lowest level codebase of reality itself. I'm talking about the Quantum Gravity Operating System, or QGOS for short. Have you ever wondered exactly how the universe processes unimaginable amounts of data without, completely crashing? Well, you're in the exact right place. We're going to break down the programmatic runtime environment that controls all simulated and macroscopically engineered spacetime. Let's get into it. Here's our agenda for today's Explainer. First up, the SpaceTime OS, then quantum registers and memory. 3. Wormhole networking and cooling. 4. Mira network stabilization. 5. The black hole syntax error. And finally, event horizon evacuation. Okay, Section 1, the Space-Time Operating System. What's really wild here is how directly our traditional computing concepts actually map onto universal physics. It's like a giant cosmic mirror. Just like your laptop uses an operating system to manage RAM and CPU cycles, the QGOS uses a hardware abstraction layer to manage the universal metric tensor, what physicists call GMUNO. So instead of silicone chips and motherboards, the QGOS treats this metric tensor as one massive mutable shared memory array. Basically, the universe isn't just an empty stage where things happen, it's a globally accessible database. How cool is that?
Moving on to Section 2, quantum registers and memory.
To really understand this, we need to build a strong foundation in how these 4 fundamental registers act as universal RAM. The crucial thing to grasp is how they divide the labor. First, the MET register holds the local metric configuration, so writing to this actually shifts local gravity and alters gravitational potential, literally. Next, the SLO register handles the slowness vector, mathematically flipping the speed of light to manage transmission latency. Then, on the actor side, the FOK register allocates localized energy to literally create particles. And finally, the VAC register tracks the zero-point vacuum baseline, so the system always knows what empty actually means. Now, you might be wondering, what happens when we need to bypass those standard speed-of-light throttles and send data across the universe instantly? Because as we know, you can't just push more power through a physical space channel without violating causality. That's a huge rule. That brings us to Section 3, wormhole networking and cooling. Let's actually trace the signal path from excitation registers to final extraction. By explicitly routing data through microscopic Einstein-Rosen bridges using the link_EPR instruction, the system builds these uninterceptable out-of-band networks without ever traversing physical space. Data moves right from the memory registers straight into a non-local throat. But here's the catch. We can't just leave these links open. The system enforces strict hardware limits on negative energy vectors. If you hold a wormhole open too long, the universe absolutely retaliates. And that brings us to an absolutely vital safety protocol. Opening these wormholes requires volatile negative energy, making the cool cycle instruction function exactly like liquid cooling in an overclocked PC. It halts negative operations and flushes the sector with a nanosecond positive energy burst to prevent frying the metric hardware arrays in a violent cosmic backlash. To minimize this hardware thermal damage, the system relies on pulse asynchronous routing. We're talking ultra-fast pick-a-second data bursts, followed immediately by those cooling cycles. Take a look at this flowchart. Notice how the INE and BLS registers constantly monitor this negative energy buildup. The INE register acts as a strict timer for how long negative energy has been sustained, while the BLS register tracks the mounting positive energy potential. They work together seamlessly to detect imminent system crashes, triggering a cool cycle reset right before the universal firewall activates. It's a highly optimized risk mitigation loop that keeps the whole shebang running smoothly. Which leads us to Section 4, Mira tensor network stabilization. So, to stop cosmic packet loss and phase decoherence during these crazy high-load network conditions, the OS deploys Mira tensor networks. You can think of this as the ultimate error-correcting code. When data travels through a wormhole, environmental quantum fluctuations constantly try to scramble it. Mira swoops in and acts as the crucial stabilization layer. Mira stabilizes these non-local wormhole links by compressing bulk volumetric data down to a hierarchical 2D boundary layer, completely isolating it from physical space noise. It reads the Tensor Network State Register, or TNS, and continuously computes and neutralizes quantum phase drift in real time, rapidly updating the quantum phase register. This guarantees that the data arriving at node B matches exactly what left node A. No corruption, no loss. All right, Section 5. The black hole syntax error.
Now, in standard computing, if you write too much data to a hard drive, it just pops up a disk full error, right? Well, in the QGOS architecture, a black hole is not some untouchable cosmic mystery. It's actually just a metric overflow fault caused by packing information tighter than the absolute universal hardware limit allows, a limit known as the Bekenstein bound. If left unhandled, this fatal syntax error literally creates an event horizon. The system enforces an immediate gravitational collapse, threatening catastrophic data loss via the infamous black hole information paradox. All those data blocks become completely trapped in an unindexable singularity. Talk about a worst-case scenario. Let's look at how the system saves itself in Section 6, Event Horizon Evacuation Protocol. Here is the step-by-step visual narrative of the exact workflow as trapped data miraculously escapes the collapsing bulk, right before the singularity physically locks. Step 1. Monitor the density as it nears the Bekenstein bound. Step 2. Interrupt standard threads by triggering the overflow exception. Step 3. Compact the 3D data down to a 2D boundary. And Step 4. Route it out to safety via those non-local ER-EPR links. Let's break down that compaction and routing process. The system treats the forming event horizon as a transient page cache. Through holographic compaction, all 3D indices are completely flattened into 2D boundary states. Then, extreme time dilation kicks in, decoupling the quantum phase. Finally, the system employs simulated Hawking radiation to asynchronously evict or flush this compacted data cache out through those microscopic wormholes we discussed earlier. But listen. This evacuation is incredibly risky, and we have to move fast. It's kind of like an overheating CPU throwing corrupted data. We must be super careful during this extraction because extreme observer acceleration near the horizon triggers what's called the Bogoliubov frame desynchronization bug. This changing geometry transforms the empty vacuum register into ghost actors, basically a high-frequency stream of simulated thermal radiation that threatens to completely overwhelm the thread's local cache with corrupted, unallocated data. To fix it, the system rapidly applies a coordinate normalization hook to recompile the vacuum and filter out all that noise. This table right here is your ultimate actionable troubleshooting guide. To summarize, these specific protocols are absolutely essential for maintaining core system stability during real-world catastrophic events. If you hit a metric overflow at the Bekenstein bound, you trigger a holographic evacuation. If your vacuum desynchronizes due to the Bogoliubov bug, you execute coordinate normalization. And if you're building up too much negative energy firewall backlash, you run a cool_cycle flush. Keep this guide handy. The absolutely crucial thing you should take away from all of this is that the universe's most violent, extreme phenomena, black holes, Hawking radiation, universal speed limits, they aren't magic. They are simply strict hardware constraints that our operating system successfully navigates and debugs through low-level software exploits. Which leaves us with one final provocative thought about the universal operating system to ponder until next time. If reality is running on a highly optimized, universally distributed computing architecture, complete with engineered thermal cooling and complex data evacuation protocols, who exactly wrote the original source code? Keep optimizing, and I'll see you in the next explainer.